another calculus optimization problem. I need to design a can. I need to know the dimensions of the lightest open-top right circular cylindrical can that will hold a volume of 1,000 cubic centimeters. So let's go back to my questions. What do I need to solve an application? What is the question? What will be the form of the answer, including units? So the question are the dimensions of the lightest open-top can. Okay, that's what I'm trying to find, and it has to hold a volume of 1,000 cubic centimeters. So I'm looking for dimensions, and those are going to be in centimeters, and I'm looking for the lightest. So now I go to the next step, draw a picture. All right, I can do this. I can draw a picture. Here is my can. Let's make kind of the bottom here that you can kind of see it too. Not bad. Not bad. There's my can. Now, one of the things that's important about this can is that it is open top. So there is no top. There is a bottom. It's not a tube. It's a can. So there is a bottom, but there is no top. The other thing is that it's asking me for the lightest can. So what I'm trying to do to make it the lightest is I can't really deal with the thickness of the can material, but I can deal with the area of the can material. Because I could have a can that looks like this, that's open top, and that might have more or less area. That's an ugly can, but you get the picture. That might have more or less area than this one. That determines as to, if I had a can that was like super flat, it would have even less area. But then again, it might not hold 1,000 cubic centimeters. So I have to do some maximization, minimization for this problem to find out which can is going to have the smallest area. It's not the smallest volume because the volume has been given at 1,000 cubic centimeters. So area is the thing that is going to be minimized. So what are some of the things I can add to my picture? Well, I can add that I have a radius of length r, and I have a height of the can at h, and I know that the volume of a right circular cylinder is equal to pi r squared h. And really, if you think about it, you might not know that right off the top of your head, but if you think about, well, what is a rectangular solid? What is the volume of a rectangular solid? Sorry, that's not bad. It's base times width times height. I multiply all three dimensions. Well, when I have a cylinder, the base isn't a rectangle anymore. It's a circle. So the area of the base times the height is going to be our pi r squared times the height instead of width times length times height. And I also know that this, in this particular problem, is going to be equal to 1,000. Now, the area of the can, that is equal to the area of the base, which is pi r squared, plus the area of the tube. And the area of the tube is if you kind of cut it and unfolded it, I would unfold the circumference of the tube part and multiply that times the height. So that's going to be height times 2 pi r, the circumference of a circle. So I have kind of a problem here. I know that it's the area I'm trying to minimize, but I have two variables in here. I have an r and an h. So what I'm going to do is I'm going to use the equation for the volume, and I'm going to determine h in terms of r. That way I can substitute that in here for this h and have everything in terms of r. So let's just take this piece and move it down just a little bit. Okay. And we can find out here, excuse me, if I divide both sides by pi r squared, that h is equal to 1,000 divided by pi r squared. So now my area is equal to pi r squared, nothing changed there, plus, well, instead of h, I'm going to use 1,000 over pi r squared times 2 pi r. Well, I can simplify that a little bit. It's pi r squared plus, well, I can do some stuff here. My pi's are going to cancel out, and at least one of these r's is going to cancel out. So it's pi r squared plus 1,000 times 2 divided by r, and let's just make this 2,000. 2,000 divided by r. I think I'd like a common denominator here. So I'm going to multiply this by r divided by r, and I get area is equal to pi r cubed plus 2,000 divided by r, divided by r. So that's the equation of my area. Now I have to find out, well, is there a value of r that is going to minimize that? So to do that, I need to find the derivative. So I need to find area prime. And I have a quotient here. So I'm going to have uv minus uv over v squared. So my derivative, so this top part is, let's make it clear here. This top part, whole top part here is my u, and the bottom part is my v. So if I take the derivative of u, well, that's going to be 3 pi r squared times, and then 2,000 has no derivative, it's 0. So times v, which is r, minus, I'll put that in parentheses, well, u is pi r cubed plus 2,000, and that's times, well, the derivative of r, well, the derivative of r is just times 1. And all of that is going to be over r squared. So let's see if we can do a little bit of simplification here. I have 3 pi r cubed minus, pi r cubed, that's kind of convenient, minus 2,000. And that's still divided by r squared. So I have 2 pi r cubed. I have 3 pi r cubes minus 1 pi r cubed. 3 pigs minus 1 pig, minus 2,000 over r squared, or 2 times pi r cubed minus 1,000 over r squared. That's my derivative. Now, I need to find the critical points. I can see where it's not going to exist. It's not going to exist where r equals 0. But I'm not worried about where it does not exist, because I'm dealing with an object in reality. I'm dealing with a can. And I know r is going to be something, because if it was nothing, then the can wouldn't exist at all. So I'm really concerned with what's going to make this equal to 0, and for that, I'm going to look at the numerator. Because whatever makes the numerator equal to 0 is going to be a critical point. So I have 2 pi r cubed minus 1,000 is equal to 0. I can divide both sides by 2 and just get pi r cubed minus 1,000 is equal to 0. And I can get pi r cubed is equal to 1,000, or I can get r cubed is equal to 1,000 divided by pi. And if I take the cube root of both sides, take the cube root, I get r is equal to 10 divided by the cube root of pi. Well, let's do a little bit of work with that to make sure that it's a minimum or a maximum. Let's find out what it is. But I'm going to turn it into a decimal because I don't really have any idea what that number is. So 10 divided by pi to the 1/3 power. And I get this is approximately equal to 6.83. Well, particularly because I'm getting into some kind of weird looking numbers here, I'm going to stop and check just to make sure if I think that could possibly be right. So what I'm going to do is I'm going to put my derivative into the calculator. And I did that right up here in my y equals my y1, and I'm going to graph it. So I'm going to go zoom 6, and I'm waiting, and I'm not sure what this graph is going to go. Oh, there's a line for the graph. And I can see that it is crossing the x-axis. So I have a 0 right there, and that is 1, 2, 3, 4, 5, 6, just before 7. So I'm getting pretty confident here that I have a 0 at about 6.83. Second, calc, 0. Left bound, I'll make it 0. Right bound, I'll make it 9. I don't want to guess. Yeah, 6.827, exactly what I have. So I'm feeling pretty comfortable now that I have actually found where my derivative is equal to 0. Now I just need to find out whether it's a minimum or a maximum to make sure. So I'm going to set up a number line. I'm just going to start at 0 since I don't have any negative numbers. And here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm at, 6.83, I think it was. So 6.83. Let's look to the left of that. Let's get our derivative formula right here. All I need to determine is whether it's a positive number or a negative number. So if I picked, say, I can't use 0 because 0 would make my denominator no good. But let's say I use the interval. I want to use the number 1 to test this side of the interval. I think I can do that. I would have 2 times pi times 1, which is 1 cubed, right, minus 1,000. And whatever my denominator is going to be, it's going to be positive, whether it's a negative number or not. It's always going to be a positive number. And I can see really very quickly that this is going to be a negative number, because pi times 1 is pi, minus 1,000 is going to be a negative number. I will have a negative divided by a positive. So this is going to be a negative. Now I need to find out whether this is going to be a positive, which would determine that it's a minimum. And how about if I use the number 10? Well, if I use the number 10, I can see that this would be 10 cubed. That's 1,000. 10 cubed is 1,000 times pi is going to be, well, over 3,000. It's going to definitely make this a positive number. All the positive divided by a positive. So in fact, that's a positive. So I have a negative slope going here, positive slope going here. Right there is going to be a minimum at radius of 6.83. So I've determined my radius right here. And if I'm not mistaken, the question says I also need to give the dimensions of the can. So the height is equal to 1,000 divided by pi times the radius squared. So let's see if I can do this math. The height would be 1,000 divided by pi times, well, the radius is 10 divided by the cube root of pi squared. So I get the height is equal to 1,000 divided by pi times 100 over pi to the 2/3. So the height is equal to 100, not 1,000 squared. I better fix that. I said 100, I wrote 1,000. Okay, so this is 1,000 divided by 100. So this would be, I'm going to cancel some of this. This is going to be pi to the 1/3. I hope this works. H is equal to 10 divided by, well, how about that? The cube root of pi. The height is the same as my radius. Isn't that interesting? So there is the answer to this problem.